All right, statisticians, here we'll have a nice video where we walk through the formal process of creating a one-sample z-test for P. Not really creating, performing a one-sample z-test for P. P standing for a population proportion. So we're going to carry out the full laborious four-step process, but this time in a test that has to do with proportion. So let's look at this example. Here I have a nice example. This is talking about the germination rates of seeds. How fun, right? I was just planting a garden in my yard. Hopefully we'll start growing food if we need to these days. But all right, so it says the germination rate of seeds is defined as the proportion of seeds that, when properly planted and watered, sprout and grow. Yay, right? So we're dealing with a proportion of seeds, right? A certain variety of grass seed usually has a germination rate of 0.80, and a company wants to see if spraying the seeds with a chemical that is known to lower germination rates in other species will lower the germination rate of this species. The company researchers spray 120 seeds with the chemical, and 89 of the seeds germinate. Do these results provide convincing evidence that the chemical lowers the germination rate? Right. Support your conclusion with a test of significance at alpha equals 0.05. All right. So a couple of key things here. We begin with some knowledge about other plants. Right. We apparently the germination rate for other seeds that are sprayed with this is 80%, right? And we're going to see if it gets lowered here. So we'll do a significance test. For the first part, remember, is stating and writing our hypotheses, defining our parameters, etc. So in terms of state, the very first thing I'm going to do is I'm going to say, let's let P equals the true proportion, right, of seeds that will germinate, right? Germinate, right? And then the null hypothesis will simply be that P is equal to what it is for the other guys, the other types of grass seeds. And here we're trying to see if it gets lowered, right? They're spraying these seeds with this chemical, and we're going to see if the germination rate goes below 80%, which is actually not really a good thing, I suppose. I'd want my plants to germinate, right? Okay. The only other thing I should do here is say what how I'm going to test at what level of significance, and we were actually told we should do it at alpha equals 0.05, so I'll just write that down there. I'll throw that on the edge. All right, so now we need to check our conditions, right? And so to check the conditions of this test, we need to know what they are. Well, we'll begin with, of course, the same conditions we always see. That'll involve randomness, that'll involve the 10% condition, all that. But what's the key other condition we always have to check? Something that has to do with the distribution, right? So whenever we deal with proportions, we're always thinking about large counts, right? A proportion, always large counts. So for this test, for a one sample z-test for proportions, that's what we're going to do. The large counts condition says that the distribution of p hat is approximately normal if we can expect at least 10 successes and 10 failures in our sample. Right? And so that will check to make sure we expect based on the null hypothesis. Remember, this little p naught is actually whatever we assume is the is the value of p based on the null hypothesis, in this case 80%. So if we have at least 10 expected successes and 10 expected failures here, we're good to go. Now, in a minute, I'm going to contrast that. After we're done this, I'm going to contrast that with what we did with proportions. And just really quick, there, instead of looking at what we expect, it has to do with what we observe in our sample. But I'll recap that key difference between large counts for a test and for a confidence interval for proportions when this video is done. Okay, so the key is that we should expect at least 10 successes. All right, so we're jumping ahead of ourselves slightly. Let's write all the other conditions. Right, so we're going to do a one sample z-test for proportion P, right? And the first thing we'll have to check is randomness. And so we're going to say they spray 120 seeds. Well, in some ways, this is going to really be an assumption. We're going to have to assume that the 120 seeds represent a random sample. I mean, I don't know. One seed is pretty much the same as any other, right? I have no idea, actually. I'm not really that much of a horticulturist, botanist, and things like that. But I guess we'll have to assume that this is some kind of random sample. We'll also check the 10% condition, because I'm sure there's no way that this was without replacement. You couldn't possibly have tested the same seed twice. And so the 10% condition, we'll have to assume the total number of seeds is at least right, the seeds of this type, is at least 10 times 120, which equals 1,200, right? There must be at least 1,200 of these seeds in the universe, and I'm sure that's the case too. So, okay, we're done with the randomness and thinking about independence in the 10% condition. We could also actually add for independence that I said we're done, but I'm going to add one more thing. We'll assume the growth rate of any one seed, right, is independent of the others, right? Just to be really button things up, right? We're really going to assume that there's I shouldn't have said growth rate, really the germination rate, but the germination rate of any particular seed would be completely independent of the germination rate of any others. Okay, so that finishes off independence. Now let's do the large counts. Large counts. Now this is what's going to give us the normality, which will allow us to use z-scores in the normal distribution to calculate a p-value, right? So for large counts, we're going to have to assume, we'll have to believe that we'll have at least 10 expected successes and 10 expected failures here. Now, I don't care about how many successes and failures I actually had. In fact, I had 89 successes, but that's not what I'm going to look at. I'm going to look at what's 80% of 120, right? And so I'm going to say we do expect at least 10 successes and failures, right? And I'll justify that just really quick in a second here. If I do 10, oh, that's like really washed out. Can you guys see that all right? Here, 10 times, I don't know why it's a little hard to see. I apologize. 10, what am I saying? 120 times 0.8, that would be the expected number of successes. That was 96, right? So I could say 10, why do I keep saying 10? 120 times 0.8, right, equals 96, and that's 96 successes. And then that would mean what's my problem today? 120 minus 96 is 24 failures. And that, therefore, I expect why did I write 124? I'm having issues this morning. I'm doing it this morning. I don't know. I'm rushing a little bit. I apologize. So 96 successes and 24 failures is what I expect. Both of those are at least 10. So great success. We can go ahead and actually carry out the math of this test. So the math of this test is fairly simple, right? Remember, the do aspect of these procedures can be done entirely on the calculator. I think I pretty much will do them on the calculator. Maybe I'll show the math too here. So for do, right, we need to give at least the test statistic and the p-value. To get the test statistic will be a z-test statistic, and it will be based on taking your p-hat and subtracting the hypothesized value of p and dividing it by the correct standard error, standard deviation formula. Now, in this case, notice that we're going to use p-naught, right? We're going to use our hypothesized value for what the truth is, right? Based on the null hypothesis that p equals 0.8. We're going to do that because this is like a sampling distribution. I'm going to assume that I know what p is because my null hypothesis is assuming that p is 0.8. So notice I don't use p-hat down here. When we did a confidence interval, we use p-hat, but in a significance test, we use p. And we'll go ahead and we'll calculate this guy, and let's see what it comes out to being. So if I do, we had 80, p-hat was 89 divided by 120, right? Ooh, that's 74%. That did support the alternative hypothesis because that was less than 80%. That's good. I never even checked that from the beginning. I really should have checked that in the outset, right? But I would do this minus 0.8. I got that value, and then I'll divide that by a big old square root. The square root of 0.8 times 0.2 divided by 120, and close parentheses, and I got negative 1.5975 or so, right? So that's my test statistic. And already our intuition should say, oh, that test statistic doesn't seem very big, but to get the p-value would be the probability of getting a p-hat that is less than 89 out of 120. given that P really is 0.8, right? And that would end up being the exact same thing as the probability of getting a test statistic that's less than negative 1.5975. And we could go in our calculator to normal CDF, second vars, there we go, normal CDF. And I'll do, since this is less than, I'll just use the normal distribution, or I'll just use the standard normal. So do negative 99999. I'll put in my test statistic, negative 1.5975. The mean is 0, standard deviation is 1 because I'm using the test statistic. And I got about 0.0551 as my p-value, right? And so let me go ahead and label that. This was my p-value. Whoa, this marker is like getting beat up. It's like tips all bad. But anyways, so here we go. Here we got our test statistic. Here we got our p-value. Now, just as an aside, I did this in a very long way. I showed all the formulas and did all the math by hand. We could have done this much quicker just doing it right in our calculator. So let me show you that real quick. Remember how if you hit stat, focus on the screen here. If I hit stat and go to tests, if I go down to where it says one prop z-test, because I did a one sample z-test for proportion, I could go and I could put stuff in. And actually, I did this earlier. For P naught, I'd put in 0.8. For X, that's the number of successes I had. That's 89. My sample size was 120. I would do less than and calculate in Shazam. Boom. Notice I got the same junk, right? It's all there. It even tells me what P hat was in case I hadn't calculated before. Isn't that nice? So great. So anyways, here's all the formula stuff, but the calculator would have showed the same thing. So here we go. Now, the last step is for us to draw a conclusion, right? Conclude our test, right? Let's conclude the test. Well, the first step is to say, all right, compare the p-value to our level of significance. And I would say since the p-value of 0.0551 is, well, what was it? Remember our level of significance is 0.05. And so this is greater than 0.05, like which was my alpha. What do? Do I reject or fail to reject? I fail to reject the null hypothesis, HO, right? Which is a little sad. It was actually really, really close. 5.5% versus 5%. Oh my gosh, I was so close to rejecting. But no, I did not have significant evidence. And so let me finish off the statement. That was my first statement. The second statement, I'll say this. Therefore, these data what? Do not provide significant, that says significant. I'm writing too fast. Significant evidence that the germination rate is less than 0.80, right? When they get treated with this stuff, right? So there we go. There's our full thorough test, where we first wrote our hypotheses, defined our parameter, we identified the test procedure, we checked the randomness condition and independence, we checked large counts because we were dealing with proportions, and to get normality, we always use large counts. Then we just showed the test statistic and the p-value, and we drew a conclusion. So beautiful, right? Just a couple of side notes, right? Well, a couple of key things to think about here. Well, one was we were very close to rejecting, right? Maybe we should have rejected, right? We're so close to rejecting that I feel like maybe we could have rejected, and maybe if we really should have, maybe the germination rate really has been lowered. I mean, 74, we got the p-hat was like 74% or something like that, right? P-hat was like 0.741 or something. That is definitely less than 80, and so it felt like we were on the edge of getting significant evidence. So what we really had potentially here, maybe if we should have rejected and we didn't make a type 2 error, which we might have made here, but if we did make a type 2 error, that means we had a lack of power in our test, right? We had a lack of power. We would have been great if we had more power. We had our probability of rejecting the null hypothesis was a little low. So how could have I maybe gotten more power to this test, right? Well, I could have simply picked a larger alpha, right? I could have maybe done alpha is 0.10. And if alpha was 0.10, I surely would have rejected the null hypothesis, right? But that's not that satisfying. That's just saying I'm going to come up with a weaker criterion. That's not always, all that satisfying, because I also don't want to make a type 1 error. And in this case, I certainly didn't, because I failed to reject. Let's say again, I should have rejected. Then my lack of power, I could have increased my power. I could have I could have used more seeds, right? I could have used more seeds. I could have increased my sample size. N could have been some bigger number. Like I did 120, but what if I did like 300, right? That would have given me more power. Or what if I did 500 seeds? I mean, why stop there? It's like seeds aren't that expensive. Go ahead and treat some more seeds and then give yourself a more powerful test. And then maybe we would have found that there was significant evidence here, right? And those are the two things that are under my power. Now, of course, the other thing that affects power is the effect size. But in this instance, I don't really, like I said, I could hypothetically try to calculate what power is based on like what P might actually be if the alternative hypothesis is true. But in this case, I mean, it's clear that P is already whatever the heck it is. I don't get to choose it. These are the only two things that are completely within my power in terms of trying to increase the power, no pun intended. All right. One fun fact, actually, I'll throw in here at the end of the video as well, too, so hopefully we don't run out of time, is to say, what didn't this significance test tell me? All it said is that I failed to reject the null hypothesis that P is 0.8. But notice that that's not a ton of information. A confidence interval actually gives us a lot more information, because it actually gives me an estimate of P, right? And so let's calculate a quick confidence interval. If I hit stat and I go to tests, and if you remember, I did a 1 prop z int. Let's see here, where's 1 prop z int? And I put in all the same information, and the calculator's smart. Notice that in this case, I might do a confidence interval at 90% confidence. Now, why 90% confidence? I just did a left tail test at 5% significance. That would mean that my alpha over here was like, over here on the left is 0.05. Well, if I did a significance test with 0.05 on the left, you could always think that confidence intervals have to do with what's in the middle. But if there's 5% on this end, and this tail, then imagine that there was another tail here where there was also 5%, and there would be 90% left in the middle. And so a left-tailed test at 5% significance is kind of equivalent to a 90% confidence interval. So I made a quick 90% confidence interval. I could hit calculate, and we got 0.67594 to 0.80739, right? Now this 90% confidence interval gives me an estimate for P. This is an estimate for P. And notice that 80% is still just barely in this estimate, right? 80%, which was my hypothesized value. This significance test, this confidence interval would be consistent with the significance test. We would fail to reject. But notice it gives me an estimate. Now, it's a pretty enormous estimate. It estimates that the actual germination rate of these seeds is somewhere in this interval, from about 67.6% all the way up to about 80.7%, right? And so what we'll see here again is that this massive confidence interval also communicates to me the lack of precision that comes from, say, my sample size, right? If I wanted a more powerful test, I could increase the sample size. Also, a good reason to increase the sample size would be if I made a confidence interval to get myself a much narrower interval, so that I'd be able to have a much more useful estimate of what P really is. Now, just again, as a quick aside, for us to make this confidence interval, we would go through the same 4-step process as we did a minute ago, right? We would define our parameter, except instead of saying we're doing a test at 5%, we would do a confidence interval at 90%, right? Everything that we'd have to check here is basically the same. The only thing that would change is large counts. If I did large counts for a confidence interval, right, then I would have had to base it on how many successes we observe, right? Not how many I expected. Because technically speaking, in a confidence interval, I don't necessarily even know what to expect. I don't know what P is, right? Unlike in a significance test where I have a hypothesized value for P, right? I'm assuming that P is 0.8, and therefore I'm using that to calculate my test statistics and stuff. Here I make no such assumption about P. I don't know what P is, right? I mean, I'm going to evaluate a claim about P, but I don't know what P is. And so since I don't know what P is, I can't use it to say how many successes I expect. I'm going to base it entirely on what I observe, and what I observe has to do with P at. So in this instance, instead of the actual number of successes, I would look at the, instead of the expected, look at the actual. I actually had 89 successes in this sample, right? And then, of course, 120 minus 89 is 31, and I had 31 failures. And for a one prop Z int, this is what justifies the large counts condition. Have a beautiful day. Giddy the heck up.